Definition of rank of a matrix. The dimension of row or column space of a matrix is called the rank of that matrix. It's denoted by rank of A. To find the rank of the matrix, convert this to a row echelon form using elementary row operations. So for example, you have this matrix. You want to know what is the rank of the matrix. So first of all, the pivot is 1. We don't have any issue there, but this guy must be equal to 0. So you're going to multiply the first row by -2 and add it to the second row. This is 0 as well. Applying elementary row operations, it gives you this new matrix: 1, -2, 0 and 1, 0, 1, 1 and -1, 0, 0, 1 and 2. So you basically have 3 non-zero vectors. So you're going to say that, hey, the rank of this matrix is equal to 3. Why is that? Because the row space of matrix is of dimension 3. It is spanned by 3 non-zero vectors. So basically, you're going to say that the rank of A is equal to 3. The definition of null space and nullity of a matrix. Suppose A is an m by n matrix. The set of all solutions of a homogeneous system of linear equations Ax equal to 0 is a subspace of the n space, and it is called the null space. It's denoted by n of A. So n of A is the set of all vectors like x such that A times x becomes 0. The dimension of null space is called the nullity of matrix A. Let's take a look at the short proof. How do we prove that this guy is a subspace? Remember the definition of subspace. First of all, it must be non-empty. It is non-empty. Why is that? Because it already has x, which is equal to 0 vector. Any matrix times 0 vector is equal to 0. So this set is indeed non-empty. Now we need to show that it is closed under addition and scalar multiplication. So you're going to take 2 vectors and show that the summation of those 2 vectors is also a member here. It's this. And then you're going to take the scalar multiplication of x and then show that cx is also a member here. But to show that these 2 are members here, you need to show that A times that summation or scalar multiplication becomes 0 as well. So we are taking x1 and x2 as 2 solutions of Ax equal to 0. So it means that A times x1 is 0, E times x2 is also 0, because these 2 are solutions. So now A times x1 plus x2 using matrix multiplication becomes Ax1 plus Ax2. But again, remember that these 2 are equal to 0. So the outcome becomes 0. A times x1 plus x2 is 0 vector. What's the meaning of that? It means that x1 plus x2 is a member of this set. Also for scalar multiplication, A times cx1 can be written as c times ax1. But ax1, as you can see, is equal to 0. It becomes c times 0 or 0. So you just showed that both x1 plus x2 and cx1 are solutions of ax equal to 0. You can easily conclude that this set, NA, or the null space of matrix A, is a subspace of N space. Example, find the null space of the following matrix. This is a 2 by 2 matrix. You have 2, -1, and -6 and 3. Well, you're going to apply elementary row operation and simplify this. Here you have a 2. This 2 needs to be 1. So you can divide the first row by 2. You end up with 1, -1/2. This guy must be equal to 0. So you can multiply this by 3 and add it to the second row. It becomes 0 and 0. Very good. We're looking for all x vectors such that a times x becomes 0. System of equations corresponding to reduced echelon form is x1 plus -1/2 x2 equal to 0. So this is basically saying that, hey, I'm going to multiply a by x and set it equal to 0 and find all of those x values. So instead of just multiplying ax and set it equal to 0, we're using the reduced form. So 1, -1/2, and 0, 0 multiplied by x and set it equal to 0 and solve for those. You get x1 plus -1/2 x2 equal to 0. But you have one equation in two variables. What's the meaning of that? It means that you have to introduce a parameter. You can take x1 to be t. T is a real number, and x2 becomes 2t. So the solution are of the form t and 2t, where t is any real number. So n of a becomes all of these vectors, the set including t and 2t. T is a real number, and then ax becomes 0. The dimension of the solution space is 1, because basically you can factor out this parameter t and you end up with one vector 1 and 2. The basis is the transpose of 1 and 2. So the rank of the matrix is 1. The nullity of the matrix is 1 as well. Find the null space of the matrix below. We're looking for x vectors such that ax becomes 0. But before doing this multiplication, we're going to write this in reduced form. Ax is equal to 0, but we're going to apply elementary row operations to reduce this. If you write this in reduced form, you see you end up with a nicer matrix, 1, 2, 0, 3, 0, 0, 1, 1, and you end up with a 0 row. So if you write down the system of equations, you have 1 times x1 plus 2 times x2 plus 0 times x3 plus 3 times x4, and it is equal to 0. On the right-hand side, you have a 0, everyone. And from the second row, 0x1 plus 0x2 plus 1x3 plus 1x4 is also 0. And the last row doesn't give us anything meaningful. Of course, we have two equations with 1, 2, 3, and 4 variables. We have to introduce some parameters. Let us set x4 equals to t. So you can write x3 in terms of t. And let us introduce a new parameter like s for x2, because you already have x4 equals to t. So x1 becomes -2s minus 3t. Well, what's the meaning of that? It means that, hey, that x, x1, x2, x3, x4 can be written as these parameter combination. The very first one is -2s minus 3t. Just write it here. x2 is s, and x3 is negative t, x4 is t. So you can separate these two. You can write s times negative 2, 1, 0, 0, plus t times negative 3, 0, because this guy doesn't have any t, minus 1 and 1. So here you have a linear combination of two vectors. What's the meaning of that? It means that the basis for the null space of A consists of these two vectors, and the rest of the solutions can be written as a linear combination of these two vectors. In other words, these two vectors are solutions of AX equal to 0 and all linear combinations. So since you have only two vectors, it means that the nullity is 2. Some important observation: n, or the number of column of a matrix, can be written as the rank of the matrix plus the nullity of the matrix. Super important observation here. So we can go back to previous examples and actually show that n, or the number of columns, is equal to rank plus nullity. For example, here you have 1, 2, 3, 4 columns. The rank of the matrix is the number of non-zero rows, which is 2. And we just showed that the nullity is also 2, because you end up with just 2 columns. So the number of columns of the matrix is equal to the rank, which is the number of non-zero rows, plus the nullity, which is the number of solutions for the null space N of A. Or basically, the vectors that you can take, the linear combination of them, and write down the rest of these x values. We're lucky here, we have two nice vectors that span the null space for this matrix. Find the rank, nullity, and basis for the column space. So you have this matrix, you have 5 columns. So n is equal to 5. There is no doubt there. We're looking for the rank and the nullity of this matrix. First of all, you can take this matrix and write it in row echelon form. This becomes 1, 0, negative 2, 0, and 1. Then 0, 1, 3, 0, negative 4. And the third row is 0, 0, 0, 1, and negative 1. And you end up with a 0 row. So you can basically say that, hey, the rank of the matrix is equal to 3. So obviously you can do the algebra and conclude that the nullity is equal to 2. But let's take a look. B has 3 non-zero rows, so the rank of A is equal to 3. You can easily do the subtraction and find the nullity, which is 2. Please note that for the column space, we're working with the columns, or you can write this guy as a transpose of the matrix and then do the elementary row operations, write down the row echelon form, and so on. But it doesn't change these facts, everybody. The first, second, and the fourth column of the matrix, they are linearly independent. So what's the meaning of that? It means that you can take A sub 3 and A sub 5 and write them as a linear combination of these vectors. So basically you have 3 independent vectors. It means that your column space has dimension 3. So it's an important observation. The rank of A, when it comes to row space, is 3. The rank of A, when it comes to column space, is also 3. because you have three linearly independent vectors. If you apply elementary column operations or convert this guy into transpose of the matrix and apply elementary row operations, you again end up with three non-zero columns. And these three vectors form a basis for the column space of A. So the rank is also 3.